morning, I'm Monse Ferrer, and with Gerard Rodrigo and Maria Isel will be presenting Boson sampling, a quantum challenge. Let's start by understanding why Boson sampling is important. In class, we've learned about quantum algorithms like shorts that solve specific problems much faster than classical algorithms. However, building a full-scale quantum computer to run such algorithms is very challenging. Issues like controlling quantum states, mitigating noise, and scaling up qubits make this a monumental task. But here's the exciting part. We don't need a fully working quantum computer to prove quantum supremacy. Instead, simple quantum systems can perform specific tasks that classical computers can't handle. Boson sampling is one of these tasks. It uses photons to solve a highly complex problem that classical computers struggle to compute efficiently. To understand boson sampling, let's begin with an analogy, the Galton board. You drop balls and they bounce left or right as they hit the pegs, eventually falling into different bins. The distribution of balls across the bins depend on the classical probabilities of the path the ball take. This Galton board is like a classical analogy for what happens in boson sampling. You substitute the balls for photons, the wooden board with pegs for an optical linear circuit made with beam splitters and phase shifters, and the beams for photon detectors that will tell you if there is a photon or not. However, having the Galton board in mind is not enough to understand how boson sampling works. In Boson sampling, the distribution of photons across detectors is determined by quantum interference, making it exponentially more complex to predict compared to the classical Galton board. An example of quantum interference happens when two indistinguishable photons meet at a beam splitter. If we run the experiment, they can either go one way or another. So photons are always detected on the same path. This is called the Hong-Mandel effect. Let's take a closer look at what boson sampling is and how it works. First, let's talk about the input configurations, which are described using focus states. A focus state specifies the number of indistinguishable photons in each mode of the system. Next, these photons are sent into a linear optical network, which consists of devices like beam splitters and phase shifters. The entire network is mathematically represented by an m times m unitary matrix U. This matrix describes how the input modes of photons are transferred into output modes as they travel through the network. At the output, the photons emerge in different configurations, also described by focus states. The goal is to calculate the probability of observing a specific output configuration. Here's where things get tricky. The probability of any particular output is proportional to the square of the permanent of a submatrix of U. Now, what's a permanent? It's a mathematical quantity similar to a determinant, but much harder to compute. While determinants are efficient to calculate, the permanent requires summing over all possible permutations of the rows and columns of the matrix. This is what makes boson sampling computationally difficult for classical computers, but natural for quantum systems.
Although being conceptually simple, boson sampling experiments generate highly entangled states reaching a level of complexity way beyond what existing classical computers can handle. Given an initial state, a classical computer can't tell what the output state is going to look like, or more precisely, the probability distribution. Not only that, but output states are not even verifiable. That means that given the statistics of an experiment obtained in the lab, a classical computer couldn't even tell whether such a result was feasible for the system or if there were any malfunctions. The explanation for this is that to find the probability of each output state, one must compute the permanent of a matrix as we saw previously, and this operation is very expensive. Matrix permanent computation is considered a class hard P problem, which is a high class in complexity theory. While the computation of its brother, the determinant, grows at the polynomial rate respect the size of the matrix, the permanent does so at an exponential rate, escalating very quickly when considering larger setups. What this means is that boson sampling devices can perform operations no existing computer is able to do, setting them at an advantage. Which brings us to the experiment held in 2020 by a team at the University of Science and Technology of China, where a significant advancement was made. They developed a photonic quantum computer named Yuzhang, which successfully implemented boson sampling with 76 detected photons. The researchers claimed that generating the same number of samples with a classical supercomputer would require about 600 million years, whereas Yuzhang accomplished this in seconds. This achievement marked a significant milestone in the field, as it was one of the first instances where a quantum device outperformed classical approaches in a specific computational task, shining light on practical quantum computing.
Now I'm going to explain some several reasons why Boson sampling is important. The first one is demonstrating quantum advantage. Quantum advantage occurs when a quantum system solves a problem faster or more efficiently than any known classical algorithm. Boson sampling is a prime candidate for showcasing this because simulating the behavior of a large number of bosons through a complex network is computationally intensive for classical computers. By demonstrating quantum advantage, Boson sampling proves that quantum systems can outperform classical systems in certain specific tasks. Another reason is because of its simplicity and feasibility. Unlike universal quantum computing, which requires a highly controlled environment and sophisticated error correction, Boson sampling can be performed with simpler setups using linear optics. This makes it an accessible experiment to test quantum theories. Its relative simplicity allows researchers to experiment and gather results without the need for the complex error correction required in universal quantum computing. The third reason is because of the computational complexity. Boson sampling helps researchers explore the boundaries of classical and quantum computation. The problem is related to a classical of problems known as P-hard, which are extremely difficult for classical computers to solve. Understanding why classical computers struggle with Boson sampling helps scientists understand the limits of classical algorithms and the unique capabilities of quantum systems. And finally, it is important because of the technological advancements. Research in Boson sampling propels advancement in photon generation, detection, and manipulation, which are critical for future quantum technologies. It provides a hands-on platform for educating new quantum scientists and testing early-stage quantum devices. I'm going to talk about some real applications. It can be applied in quantum chemistry. Gaussian boson sampling, which is a variant of boson sampling, can be used to calculate the vibrational spectra of molecules. These spectra are important in understanding the behavior of molecules and their reactions, which has applications in drug discovery, material science, and chemical engineering. It can also be used in some optimization problems, such as those in logistics, finance, and network design, which involve finding the best solution from a large set of possibilities. Quantum algorithms inspired by boson sampling could offer more efficient ways to tackle these problems compared to classical algorithms. And finally, quantum systems based on boson sampling principles might be used to speed up certain types of machine learning tasks. For instance, sampling for complex probability distributions is a common requirement in machine learning, and quantum systems could perform this more efficiently. Although we won't go into detail, boson sampling also has applications in areas like cryptography, photonics, data analysis, and quantum information processing.
Let's recap. Boson sampling is a linear optics quantum computing approach that uses Fock states of light. An initial state of full and empty modes is run through a net of beam splitters. The output state is random, with a probability of each being proportional to the permanent of a matrix related to the setup. Such quantities are very expensive to compute, that's why it is impossible to simulate. The Jiuzhang experiment conducted in China was a milestone for the field, as it was one of the first quantum devices to present a real quantum advantage. This technique is also important because it's simple and easily approached. It is testing our knowledge and computation complexity and sets the foundation of still to be developed technologies. Its applications are still to be fully exploited, but it can be used as a tool in science as well as optimization problems for machine learning. Thanks for watching.